on time. So welcome everyone. Good morning, good afternoon, good evening, wherever you are. So this is our weekly International Geoenvironmental Engineering webinar series. I am the host. My name is Krishna Reddy. I'm from University of Illinois at Chicago. So you have my contact information here if you have any questions. So we're going to cover, wide range of topics in geoenvironmental engineering. Anybody who's interested is welcome to attend. So as some of you recall, we had a year-long webinar, weekly webinar series last year. And good thing is we have recordings available on YouTube channel. Later on, I will put this link in the chat box so everybody can have it. So we received, very positive feedback from attendees, and many students, researchers, and practicing professionals requested that I should continue this webinar series. So, so that's the reason why I decided to have towards the end of this year. I thought people are sick of webinars, so I wanted to, not to attend, not to organize all of this if people are not interested. So this is the webinar series that we have, October, December. So fantastic presenters. And then we had the 2 webinars before, and this is the 3rd webinar. And you have all the information, the website that I mentioned here. So today's webinar, as of this morning, we have 612 registrants for this webinar. So I request everyone to mute your mic and switch off your video. Type your questions in the chat box at any time during the presentation, and our presenter will answer at the end of the presentation. And thank you again, everyone, for joining this webinar. So today's topic is very, very interesting. Yeah, it's a successful solidification stabilization of freshwater sediments impacted by an organo-arsenic herbicide. As you all know, many of our previous presenters are from academics. And today we have experienced practitioner, Dr. Dennis Grubb. He's the technology fellow at Jacobs Engineering, Global Environmental Solutions, and in Philadelphia area, USA. So just a brief bio of Dr. Grubb. He is, as I said, he is a technology fellow at Jacobs. So previously, he was the Vice President of Research, Development, and Technical Sales in Phoenix Services. And before that, he was a Senior Principal Technologist, Senior Project Engineer with another consulting company, major company CH2MEL. And before that, he was a Director, Environmental Technology, Sustainable Geotechnics at CETCO. Before that, he was a Senior Associate Shenable Engineering. And then before that, he was Assistant Professor in the Department of Civil Engineering at Georgia Tech. So Dennis received his BS in Civil Engineering from Drexel University, and Master's in Civil Engineering from Stanford University, and Master of Engineering and PhD degrees from UC Berkeley, all covering civil, geotechnical, environmental, and chemical engineering. So Dennis has more than 30 years of combined academic research and engineering consulting experience in various topics. The one which I can think of him being very, very involved are environmental remediation, beneficial use of all the recycled materials. I know a lot of our participants work on waste materials. He worked on many different types of waste materials, stabilization, solidification, which is the topic of today's presentation. And he also worked on environmental forensics. So he has very good publications on a lot of his research projects. So he is the recipient of NSF Career Award, NSF NATO Postdoctoral Fellowship, Fulbright Fellowship, and he received 2014 ASCE Samuel Arnold Greeley Award. And then he received 3 ASCE Best Practice Paper Awards. He writes really, very well. All his projects. So he became an ASE fellow in July 2022. So on a personal note, I say that, I worked with him on a project. He was a co-investigator on a project that we worked on. I actually still working on a biogeochemical cover system for landfill. So it's a lot of pleasure working with him. So you will see, what I mean by this. So he said he's not going to have his video on. So I just want to show his picture again to see how he looks. But hopefully you will come across and meet him in person in one of the future conferences. So with that one, Dennis, take it away, share your screen and go for it.
Sure, I'd be happy to. Thank you, Krishna, for inviting me to this series. In looking at the other speakers here, I am in, I'm amongst some of the, the greatest, profs in recent history in our environmental geotechnics area. So it's quite a privilege to be with you this morning. As Krishna had indicated, my expertise areas are, remediation. And when I mean remediation, I'm not talking about parts per billion or parts per trillion. I'm talking weight percent. So I have an affinity for highly contaminated systems. And also I'm an expert in the beneficial use of industrial byproducts and recycled materials. When I was at Stanford doing my MS in environmental engineering degree, I was kind of already overcommitted to working with non-aqueous phase liquids, TCE solvents, things like that. And that's when I took water chemistry, got very interested in that. And then, when I left Stanford and Berkeley, I got more into heavy metal speciation, stabilization, solidification, beneficial use, and mine waste. And I work in all of those areas because the metals chemistry is very similar. So I developed in the mid part of my career an interest in heavy metal speciation and highly contaminated systems. And this project really exemplifies one of the multi-dimensional challenges that you will receive if you're working for what I would call a tier 1 environmental company, the size of a Jacobs, where you have the ability to see very unusual wastes in very high concentrations. So this particular project is where we had a challenge in the Midwest. I'll show you the site map here in a minute. What was happening here was that this was a facility that actually made what we call Agent Blue. Some of you may have heard of Agent Orange that was used in Vietnam during that war. This was its cousin, and it was also a very concentrated herbicide that was arsenic based. And so this introduced a number of challenges with immobilization of that arsenic to clean up a turning basin, which you can see in the background of this picture, and send that material to a non-hazardous landfill. Krishna indicated that I previously worked for CH2M Hill. CH2M Hill was acquired by Jacobs while I was at Phoenix Services, which was a steel mill services company, and where I was beneficiating steel slags, iron making slags, and stainless steel slags. In any event, what you're taking a look at here is these are the cement pigs. These are frac tanks for water. These are the cement silos for the stabilization solidification system. Over to the left, we have a crane on a barge that was used to remove sediments from this turning basin, put them in a scow, bring them dockside. This is actually the unloading bin where they arrive after they get taken off the scow, and they're putting it through a small batch plant here to do stabilization solidification. This plant was actually redesigned because I joined the project when in fact the project was shut down. Sevenson was on standby at probably, if I remember correctly, maybe $100,000 a day, because the mix design that was implemented for this project did not work, right? So I was recently joined to CH2M Hill, and they threw me into the fire to help them solve this arsenic immobilization challenge and get the project back on track. So I had the senior management of CH2M Hill calling me daily, asking me if I had solved the problem. So as a new employee, you can imagine the pressure that I was under. So you find out who you are real fast. At Jacobs, we have a culture of caring moment and or a health and safety moment when we start each presentation, so this will be no different. And so what I want to draw your attention to here this morning is some of the hazards associated with cement, which is central to my talk today. So cements, Portland cement specifically, is used as a stabilization solidification reagent in many applications. It's used commercially for making concrete, cement block, other solidified materials. And so it's the primary active ingredient in that mix that gets you to pH 12.5 or 13, where the cement reactions are initiated and you begin creating calcium silicate hydrate minerals and others that develop the strength and lead to the metals immobilization. So because it's a powder and because it's strongly alkaline, there are a number of issues associated with this that are primarily skin contact and respiratory if you inhale that. And so at that pH, you begin to dissolve mucous membranes. And so the main concern here is that, you'll get this in your eyes where it will burn and be an irritant. Respiratory, it also contains silicates, crystalline silicates. So there's concerns about that. And so the appropriate PPE for dealing with cement powders, if they're out in the open, which would be in a dry mix situation, particularly on a stabilization solidification job, or Jeff Evans does, slurry walls, for instance, if you're putting in a cement bentonite slurry wall. Most of these are contained in pigs and pneumatic systems, so you don't really have to worry about it. But if you're doing dry mix stabilization solidification, it is going to get airborne, and you need to stand up when and wear the appropriate personal protection. So goggles, gloves, respirator, if you're in heavy airborne dust inside, for instance. Okay, that said, let's take a look at the project area. Here we are in upper Wisconsin, not far from Green Bay, so maybe an hour north of that. We're actually looking at the state line here. So the industrial facility that we're talking about is the blue-white dashed line. They had what they called here a former salt vault area, and so they were manufacturing this herbicide, Agent Blue, for the military and others. And so the end product of, or a byproduct of that manufacturing process was a salt material that had trace to moderate levels of arsenic contamination in it. And so sadly, this was stored outside, and the combination of rain, snow with salt basically means you will dissolve that salt and mobilize it. And so what they had was a dense aqueous plume. So this would be like a sugar solution or salt solution, fully miscible with water, that began leaking through the concrete pad, the cracks, et cetera, got into the groundwater table and upwelled into the turning basin and the transition areas of this freshwater river area, the Menominee River, which basically right off the page is Lake Michigan. So the main issue here with a dense aqueous solution is you don't know where this is going to upwell. And so you can almost think about the preferential flow paths being like, blood veins, for instance. And so the challenge with this project was essentially that, you could move 5 feet over and you would go from basically clean with an arsenic, from an arsenic perspective, to screaming hot with arsenic. And so the variability of the sediments that you would be pulling up and putting into the scow on a bucket by bucket load was tremendous. So how do you effectively manage that in a remediation project where you're trying to take arsenic impacted sediments, bring them to the dock, dewater them, and because we're very congested here, this was about 1.5 acres, export these to a municipal solid waste landfill with a non-hazardous classification. And what that means in the United States is that your toxicity characteristic leaching procedure, or T-CLIP value, is less than 5 milligrams per liter arsenic. So we needed to achieve all of that in basically 72 hours to get that stuff off site to avoid additional site congestion. So part of the challenge with this, as I indicated earlier, was the variability. So we had two main sediments that we were dealing with. We had a soft sediment which had a lot of organic matter in it, and what we called a semi-consolidated material. Both of these were sandy, silty materials, but the soft sediment had twice as much organic material in it, and as a result, it was very concentrated in arsenic. So you can see the quantities to be removed based on the bathymetry, where the soft sediment in the turning basin was about 43,000 cubic yards. In the transition area, it was about the same. I hope you can see my cursor here, 42,000. But look at the concentrations, right?
Dennis, can you right click it and get that other?
Yeah, let me get to that pointer option, laser pointer here.
Yeah.
There we go.
That
Right, so in the soft sediment had, we had about 86,000 total between the two main areas. The semi-consolidated material, which was more of a free draining sandy material, had about 10 times less the contamination level. So you can see here, again, variability wise, I have basically 2 milligrams per kilogram up to 20,000 with an arithmetic mean of 2,900. The transition area was not really that contaminated, but again, how do I know what I'm picking here? This was a really big challenge. So chemically speaking, the two main active agents in the agent blue were dimethyl arsenic acid and monomethyl arsenic acid. And the solubilities of these were 2 million in the case of DMA, and in MMA, it was 256,000 milligrams per liter. So I ask you, what are you going to do here when your T-clip limit is 5, right? These are enormous numbers. So it was a significant technical challenge to devise a method, right, to get below 5. So let's take a look at some of the physical and chemical properties, very high moisture content materials on that soft dredge material. So we picked 2 surrogate soils from an area called B6 and B4. They were, almost liquid. The loss on ignition, which is an indicator of organic matter content, was 15 to 20. It was pH neutral. It was fairly plastic, and a lot of that had to do, in fact, with the organic matter content because it classified as an SM. But again, our average, for this sample that we used for the treatability study was about 6,300 milligrams per kilogram. The B4 material was about 4,200. The semi-consolidated material, which was more of a poorly graded sand or an SW material. These again were more freely draining, but yet you still had, even in a sandy material, up to 32 milligrams per liter T-clip. In the case of the B6 material, you're about 34. So, the challenge here is it didn't matter if you had a lot of fines or a plastic material or not, it was equally concentrated in both soil types. So you couldn't use just straight geotechnical characterization information to tell you what material you were dealing with and have that be correlated with the leachable characteristic on arsenic. So when you do a treatability study, what you need to do is you need to mimic what's going to happen at the site. So if you don't model the site processes with your treatability study, you are going to end up with a solution that does not work in the field. I stress this to everybody. I lead a lot of treatability study work at Jacobs. And if I was to tell you the single most important issue that is always overlooked is making sure the treatability study mirrors the field processes. So what did we have to deal with material-wise? The soft dredge material and our semi-consolidated material, both of these up to about 30 to 40 milligrams per liter T-clip arsenic. The site constraints, and this is where you transition from science to engineering. We were only allowed to use 2 reagents because we needed a compact stabilization solidification system. We prefer dry reagents because we're obviously trying to dewater something with a moisture content north of 150 moisture points. We needed to ship the material off-site in 3 days, so 72 hours to avoid congestion. We had 11 bins with 1,700 cubic yards capacity each. And if you got out of cycle and you failed your arsenic criteria on those, the site backed up immediately. And in fact, the site was completely shut down because all the bins were contaminated when exceeded the T-clip limit when I joined the project. So the idea is get that off-site as fast as you can. And so when we looked at our treatability study, we looked at curing intervals of 1 hour, 1, 2, 3, 7, and 28 days. The early times to manage the materials and expedite their removal from the site, but 3, 7, and 28 days for compliance to ship offsite, and then long-term compliance at the landfill. Okay, so you can imagine you can develop a scheme where you passed the T-clip on day 3, but by 28 days it failed at the landfill, and then it was a problem at a landfill. So we had to demonstrate that whatever we met at 3 days at least lasted through 28 days when the material was fully cured, okay? So in order to be able to ship off non-haz, you need to be 5 milligrams per liter or less. That was required at all 3 of those intervals, as I indicated earlier. But the paint filter test is a test that looks at the expression of free liquids from a solidified material. So what you actually want to monitor here and take account of is traffic vibrations. So this is a static test, but we've developed a test that enables you to look at the liquefaction of that material due to transport vibrations going across the road, because a lot of wastes will in fact liquefy and begin leaking and when they're out on the road and be rejected at the landfill. So we also needed to make sure that that was not only something that passed the paint filter test, but you could work that material with conventional equipment. So these two kind of go hand in hand, but the materials handling aspect of that is more covered by the workability requirement, which was being basically, for all intents and purposes, non-plastic. And then the other thing that we had to do was track the dosing and the actual reagent unit costs with our dosing strategy. So the arsenic immobilization strategy, which was first and foremost, was that first we needed to understand what was happening in terms of the overall EH, pH, stability of arsenic, right? Because we needed to ensure that it was going to remain immobile for the long period. And what we realized is that the leading strategies for arsenic immobilization actually have combinations with iron. So when we superimposed iron speciation on top of this, what we realized is that we needed to be in this crosshatch region to immobilize the arsenic for our site considerations, which meant that we needed to be oxidized and we needed to be between pH 4 and 8. Usually when you're working with a stabilization solidification system and you're adding cement, you're way over here in the pH 12 and a half to start the reactions. And for long-term stability, for most projects, you want to make sure that your pH is maintained above 10. That wasn't going to work on this project. And in fact, I will show you mixed designs where we started with an initial T-clip of 40, and because we didn't get our pH right and we were strongly alkaline, we in fact doubled up to 80, which is, no bueno. So in terms of looking at reagents that we're going to be able to dewater a highly liquid material and to have combinations with iron and also sulfur, which is known to immobilize arsenic, we looked at probably 30 to 40 reagents. These are the top reagents that are listed here, and they appear in the papers in ASCE. And the key here, again, for tracking the reagent unit cost is, some of these, this one here, this EnviroBlend was $600 a ton. Some of these others, this this polymer-based thing is about $1,400 a ton, but you only need 1% of that in some cases, for depending on your project. So you have to look at the reagent dose, right, times the unit price to track the cost. And that's what we had to do. So, again, challenging material, and we did probably 200 plus mixed designs to nail down the immobilization of this arsenic and to find cost-effective solutions. So this is actually my colleague, Dusty Berggren, and those are some of the mixes there that we're tracking over 3 days to understand its workability characteristics, whether or not we'll pass the paint filter, and to pull out our T-clip samples. So let's talk about how we track that. I wish I could hide this stuff at the top. How do I do that? Because the key is up here, and what you see is we have our moisture contents that we're tracking in the leftmost column. We have our reagents, again, limited to 2, and our priority was to be adding iron into the system, and then if we needed solidification, to begin adding things like Portland cement. And then we track the paint filter, ORP or EH, pH, the T-clip fluid we were using, the ORP during T-clip, the T-clip pH, because that's the regulatory criteria, or one of them at any rate, the T-clip arsenic, right? And so green means you passed, red means you failed, and we needed to track that. We tracked it at 1 hour, 3 days, 7 days, 28 days, and then I'm showing you the reagent unit cost in the rightmost column. So let's take a look at a couple of these. So here, we're adding aqueous ferric sulfate, which seems odd. Why would I add a liquid to immobilize a liquid? But in fact, you know, all the iron is in solution. Dry reagents typically foul. So delivering arsenic and having, iron in solution to react with that soluble arsenic is important, right? So in high water content stabilization challenges, we're often adding our reagents in aqueous form to enable the immobilization reaction to occur, precipitation, sequestration, etc. Then we have our Portland cement. So let's take a look at what we got here. Remember, I said we needed to be on the T-clip between 4 and 8, right? So this ferric sulfate combination with and without Portland cement did very well, keeping us in that sweet spot on pH. And as a result, even after 1 hour of reaction, our T-clips were well below 5. The question was that going to last out to 28 days continuously? So we had a number of these fail, right? The ferric sulfate only. Part of the reason for that is we drifted out of the pH optimal range. For the ferric sulfate and cement combinations, we actually did pretty well here. And so at the upper doses, again, aqueous, we found that 25 and 30% ferric sulfate with 10% Portland, you know, got us to a successful outcome. So let's take a look at another one. This is another iron containing reagent, also with Portland cement. But here, as I said, you needed to be between pH, 4 and 8, essentially, which is very unusual for SS systems. And look at this, we are doubling the T-clip. We started out with a maximum of 40, and now we are basically 60 to 75. This was also off-gassing hydrogen sulfide because there was a sulfur compound in there, and we shut that down because of the T-clip failures and because of the hazard associated with the off-gas. Down here, we have ferrics, which is actually the dry powder version of ferric sulfate. And we began taking a look at those combinations. And again, we're very good on our pH, very good on our leach, except for the lowest dose. So we got rid of that one, but all these other ones tended to work out fairly well. At the end of the day, what we ended up recommending were the 2 black boxes on the right-hand side. What was also quite interesting was we used ferric chloride, which is from the steelmaking process, right? And that is also an iron acid and lots of iron in it. And so, it was comparable to the ferric sulfate, but actually cheaper. So we ran that through the system. And what we found was, in fact, that was actually more cost effective, but you have to pay attention to the workability. And so let's talk about that for a minute. When you're working with complicated systems, you need to have hands-on experience or somebody that you trust that is working with those materials, that is paying attention to how these systems are evolving. If you don't, you're going to pick something that doesn't work. Here is the ferric chloride. The fill line on the sediment was probably about 500 grams. We put that in there with the 30% ferric chloride, and it began oxidizing it and swelling it and poured over the edges, right? It turned the stuff into mousse, right? We also looked at, because it was so cost effective, we then looked at it with the Portland cement. That was still swelling to about 3 times the volume from its initial volume. And so, that was rendered not workable either, right? Because how are you going to get this stuff off site? This was like a mousse. You couldn't handle it. By the time we actually got it to be a solidified material that was actually workable, we broke the bank on exceeding the number of reagents we had to use. So this got kicked out, even though it was, the most cost-effective one there, but it wasn't workable. The other aspect that we had to understand is, were we generating, because it was ferric chloride, where were we generating, chlorine gas, which is why the site originally got shut down, because they were using hypochlorite to oxidize the arsenic. So here we looked at an experiment of again, putting 500 grams of the SDM mix in a jar in a water bath. We looked at the off gas of that into a graduated cylinder. And at 500 Gs, we were basically creating the same amount of gas volume, a little bit over 600 in this case, within a 24-hour elapsed period. So that would have meant that all the SDM sitting in the bins and going through the the pug mill would have been generating chlorine gas potentially and shutting the site down. When we actually analyzed what was going on here and the quality of that gas, so we put nitrogen gas into the reaction vessel, we put the off gas through impingers to scrub it, and then we analyzed that. What we actually found was, in fact, we weren't generating chlorine gas. It was basically non-detect. That ferric chloride was so aggressive, it was oxidizing all the organic material in that dredge material, and in fact, rendering it unworkable. We turned something that was a silty sand material into basically a mousse or a whipped cream that was no longer workable. So again, as I said, if there's anything you take away from this, make sure you're paying attention to what's happening to the materials as they react. All right, so now we said, okay, we came up with, because of our SDM had different characteristics from our semi-consolidated material, we wanted to come up with conservative doses based on those materials and the expected concentrations of arsenic that may be in those. So we selected a dry mix, ferric sulfate source, and the wet mix. But you can see here, depending on what you're going to get in the scow, you have a price between $19 and basically $124 per ton. And so when you run the numbers on that, we were going to treat 232,000 cubic yards or 348,000 tons of material in 2013 at a rate of 200 tons per day. So that was about 4 to 5 scows, 24/6 operations. So each scow is 500 cubic yards, and it can be highly variable in terms of what's in that scow. Each storage bin was 1,700 cubic yards. If you failed a bin based on 3 T-clips tests on that bin or that 1,700 cubic yards, to empty out that bin, retreat it, put it back in the bin was $200K. If you then failed a second time, you had to go to hazardous waste disposal at $750,000 for that 1,700 cubic yards. So significant penalties here if you did not get your dosing right and immobilize arsenic the first time. So, we were thinking we'd be using, this Ferrix 3 at 10% the whole time, but the problem with that was, or the aqueous one, when you ran the numbers out, that was almost $27.5 million in reagent cost alone. I haven't paid for one guy, one piece of equipment. That's just the reagents. No landfill tipping fees, right? Just reagents. So what could we do to control that reagent unit cost? So what we took a look at was what we call we're being regulated against the T-clip arsenic. We can collect totals information as well to help us understand how contaminated it is. Moisture content, that's a quick test. pH and ORP are also very quick tests. So the real logjam here was the T-clip test, which is usually an 18-hour extraction. So we devised a mini T-clip that we could use on-site with an on-site lab and do a rapid turn on that, so that in the decanting period, which was 6 hours for each scow to let the water come off, we would have a result and be able to say, hey, this is what dose you should apply to that scow in a real-time basis. So how did we do that? The important thing to recognize here is that with sandy, silty materials that are natural in origin, or glass-like, or high in solution, aluminum silicates, and not clay, these materials have very little buffer capacity. I actually picked up on this idea from Paul Lear, who works for a Stabilization Solidification company, because he was looking at lead leaching out of crystal, and he ran an acid extraction test very quickly and found that because glass has no buffer capacity, your pH after about 1 hour is actually the same as your pH at 18 hours. So all we had to do was rapidly acidify this material and then track the arsenic with time. And what we found was, for the soft dredge material and the semi-consolidated material, In an hour, I basically, with the soft dredge material, I had the same pH or virtually the same pH that I would if I ran that test for 18 hours. Well, that really condenses my time frame and allows real-time processing. The same thing happened on the SCM low. In fact, the numbers ended up being conservative on both of those. So that seemed to be the way out of the woods. So again, looking at the analytical tests here, full T-clip with digestion or in a screening mode where you don't do the heating for the analysis, those were going to take 20 to 22 hours. That was not going to work because then we'd have all these scows sitting out on the water, not able to be unloaded. And if you sent that out to an external lab, you're talking about a 3-day turnaround time in your analytical data. That was not going to work. On the Mini-TCLP, right, what we found is that, again, looking at the screening or digestion, what you did with a much smaller volume, and we extracted this for a half hour to up to 3 hours, what we found was we could shorten the time frame down to maybe 2 to 7 hours. So let's take a look at what happens when we look at our surrogates and their leaching behavior. So the dark line is the actual procedure. The dashed line is our Mini-TCLP in a screening mode without the heating at the end for the digestion. The open circles is with the digestion. And what we find here is that actually for the highly impacted systems, our 3-hour Mini-TCLP basically matched our 18-hour full T-clip by the book, which was what was going to be tested on our samples in the bin. So this looked like a path forward on that. When we looked at the semi-consolidated material, again, we're looking at our 3-hour T-clip because it worked for this one. How did we do with respect to the semi-consolidated material? And in fact, this value is higher, right, than what it would be it's a little bit lower than what it would be for the 18-hour, but it's basically conservative even at that levels. So we went ahead with the Mini-TCLP in the screening mode, and we were able to get our analytical results from the on-site lab within 3 hours. For the XRF, what we did with the XRF was we took a handheld device and calibrated that against the totals by the official procedure, and we came up with a calibration line. So now we're in the position where we know what the leachability is, we know what the total is, and this helps us, in addition with moisture content data, to figure out whether or not we have soft DM or semi-consolidated material, and we can begin dialing in or ratcheting down our dose to make things more cost effective. So this is a close-up of the offloading and processing area where we were, again, doing 200 tons a day. And so here you see the unloading barge, the passing material into the screens and the trash rack. That then flowed by gravity into these two cells. Excavators and took material out of those cells, passed it through the pug mill. Then the loaders, which aren't actually shown here. So this is the backside. This is looking at the two excavators, right, unloading. This is the pug mill system, and this is where the solidified solids come out, and then they are taken to the storage bins, each one of those being 1,700 cubic yards. That's what this picture is. What you see in the background is there is an excavator sitting on an elevated platform that can then reach back into that treatment cell, take the material out, swivel around 180 degrees to the opposite side, and put the material into a truck. So let's take a close-up of some of the equipment used here. This is a Senobogan materials handler. This is what emptied the scow into our screening system and trash rack system before it went into the surge tank for the excavators, which are sitting here. They take the material out of the surge bin, drop it into the hopper for the pug mill. Here's your cement silo. The ferric sulfate came in on a different line. You can't see that here. And then these loaders took the material out. This is the device that put in the ferric sulfate, the dry mix. And then here is a loader filling up a bin. This is steaming because the ferric sulfate, the combination with Portland cement, is very exothermic. So it's driving off a lot of moisture at the same time it's immobilizing the arsenic. Now, so here's the bin with the impacted material on the right-hand side. The excavator swivels around to the other side, fills up the truck that's going to the landfill. So it fills it here, then it goes through a truck wash system before it goes off-site to the landfill. So let's take a look at our processing now. And so here what you see is we were working between basically mid-May to mid-October, right before US Thanksgiving. And this is the number of days that we had various different throughputs. So our minimum was 200, probably a bad day, rainy, not able to process or solidify, up to, some of these days we were moving 4,200 cubic yards of material. So that would have been basically 8 to 10 scows, which was a phenomenal throughput. But usually it was 1,600 to 3,000, probably an average of about 2,000 to 2,400 a day. So very good throughputs. So how did we actually do our dosing, right? We've got these scales coming at us. They're going to decant for 6 hours. What can we do in those 6 hours to figure out how to dose that, get it through the pug mill and into the storage bin to start drying out? So what you see here is this is a particular scow here, scow number 29. We pull our 10 QA samples from the scow. We do the moisture contents. We do our XRF to get our total arsenic. We do our Mini-T clips in the on-site lab, and we get those averages here. And so as you take a look at this first one, we had moisture content from 23 to 75. Our totals were about 360 to 3,500. Our T-clip max on this one ended up being about 40, but you have a huge spread here in terms of, your T-clips. So we were concerned that, hey, with such variation on this, what we really needed to do was even things out. So we sent this to be rehomogenized. So they remixed it, we retested it. So now our maximum is only 28, our minimum is 13, so our average is 19. So our average has gone up, but it's a much more uniform distribution of materials, including the totals, which are much less erratic. This was 3,500, now our top value is about 1,200. So now on the basis of this, we treat it with 25% aqueous ferric sulfate, 10% Portland, and then here is our bin compliance testing before exporting for the site. So you see that we had basically 3.26, 1.38. Our average ended up being 1.72. But if you had one failure on this, it had to be reprocessed, right? So our pH is, again, right in the middle of our targeted range, about 5.2. So this was a pass. After we rehomogenized the scow, let it sit for another 6 hours, brought it back, retested. Scow 42, we actually had on this one 6,300 milligrams per kilogram and a T-clip of 72. So we're way above our treatability study, right? We're almost double. We're like, that's not good. Let's go remix that one. We got it down to 50 as our hot spot. Okay. We evened that out. It was basically the same average, but now, these doses are much more consistent except for that hot spot. And so we actually went above our recommendation for the treatability study. We added an additional 5 weight percent of the ferric sulfate just to capture that higher level of arsenic. And again, that was successful. I was getting calls at 2 o'clock in the morning from the guys, in the field going, hey, you're not going to believe the kinds of T-clip values we're getting here. The highest one on the project was 195. So at 2 o'clock in the morning, half awake, I'm being asked for a dosing recommendation so they can continue moving scows through the pug mill. So it was pretty nerve-wracking, especially with the senior leadership calling us on a daily basis about how we were doing. So here's another one, scow 55. This was more of a semi-consolidated material, even though some of the moisture contents were actually a little bit higher. And what we were able to do with this one was hit this with 10% ferric sulfate and 5% Portland, which was our preferred blend for the semi-consolidated material. And again, that was a pass. So let's take a look at some of the performance statistics. Here are the number of initial scow samples and their moisture content. So log normal distribution on this, but we had everything from, down to 10% to up around 700. So, we had to track that. This is the moisture content, right from the scow as a function of the Mini-T clip and our detection limits and our T-clip criteria. We had 2 correlations, as I showed you, for the XRF. The one that was over 5,000 was really for the soft dredge materials. So I'm showing you what those actual points were that were probably really soft SDM. And then the rest of these were, most of the rest of the values were basically below 3,000 when we had our correlation change. So here is our XRF by the arsenic information totals versus our Mini-TCLP. What we're actually showing you in this diagram or plot is our sediment surrogates that were used for our treatability study. And at the end of the day, we actually picked pretty well. These are our 2 soft dredge material, actually 3 soft dredge material samples, because we had another one mid-project. And then these are our 2 semi-consolidated materials. And so you can see we had a number of hits up here, but these are initial hits before reblending, right? So when you reblend those, you knock those back down and we were able to treat them. This is the bin compliance. So here is your total arsenic in terms of milligrams per kilogram. Here's your official TCLP arsenic. And so what we had here was, again, I said any single value over 5 milligrams per liter created a fail. We had 4 of those, which then meant that we had to reprocess the entire bin, even though 16 of those samples were compliant from those same bins. Didn't matter. You had 1 failure, reprocess. So after reprocessing, you can see all the open squares are what we did. And so in effect, all of the black solid samples shifted to the open squares and treatment was successful. We only had 4 bins that had to be reprocessed, none that went to hazardous disposal. So this is the summary of the actual dosing for the first, I think it was 190 scows or something like that, because they had to pre-purchase the dry ferric sulfate because there was a world shortage in it. So at the end of the project, they began just using that to get rid of it and didn't have optimization with the aqueous ferric sulfate. But before that transition, these are the doses that were initially recommended from the treatability study, which are the crosshatched, and the others are, you know, as we gained more information and got more comfortable with our dosing strategies, we looked at a lot of intermediate and other doses, especially this 20% dry with 10% Portland was one of the best mixes that we, ended up working with across the project. So in summary, we worked from basically 6 months, spring to just before US Thanksgiving, 232,000 cubic yards or 330 scows. That corresponded to 348,000 tons or 198 bins, right? That had full TCLP compliance on them. So 4 to 5 scows every day, 10 samples per scow, greater than 2,000 tons per day average processing, 24/6 operations. The highest moisture content was 650. The highest total arsenic, right, was almost 77,000. This is comparable to a arsenic ore. Okay, so we actually had a mining consultant working with us to help us with the treatability study initially, because nobody had seen these kinds of concentrations at an industrial site. And so we were like, hey, we're in mining space. We need somebody to help us out here. So I spoke to a guy from Montana Tech, and he helped us understand that initial EH/pH diagram and to dial things in. The TCLP high, as I said, was 195 or almost 40 times the limit. So, you know, when you're in this territory, you don't have a lot of options, and we were actually very successful, thankfully. 3,300 screening samples from the scows, that's both initial and remixed. We had 76 scows that we reblended to knock the concentrations down, and four bin failures out of 198 bins, or just about 2%. And so with that, if you're interested in more details, this is published in ASCE. The actual year is 2016. Maybe, Krishna, while I'm talking here, you could put these citations in the chat, though I think we're archived on this presentation. So you're welcome to look at this slide and pick this information up here. This won the 2017 Best Practice Award. I found this interesting. The mixed design paper actually won the award. The real innovation, in my opinion, was coming up with that rapid XRF with a handheld XRF device versus totals, and the Mini-TCLP. Those were the main engineering and analytical breakthroughs, and the real-time processing and an evaluation, but that didn't get the award. This one did. So, hey, I'll take it. But this was a project where I really, looked at myself in the mirror a lot, like, Dennis Grubb, do you really know what you're doing? And you're going to get fired tomorrow. So when you're, working on a project like this with this kind of high visibility, internally and externally, you really find out who you are. And I had an excellent team around me. I do a lot of treatability study work with Dusty. She is my right hand, really unbelievable. Drew Walter tracked all of the scows. Mr. Alm, he ran the analytical lab. He was a subcontractor, and Ben Thompson was our air guy, an analytical guy that helped us out. The other person here was Heather Ziegelbauer. Let me give her some kudos. She was the project manager, and Jeff Danko was the site construction manager. So again, just wonderful colleagues. This was a fascinating project, and I am so relieved that we got this done. And so with that, I think I'll take questions.